This might sound a little bit crazy, but I'm about to start over again. I spent like 6 hours yesterday working on this, and I'm going to start all over again. I was watching a donkey video. Yeah, I'm going to go to live streaming.
Hey, Daniel, I didn't mean to belittle your feelings. Actively right now?
Well, I just turned the mic back on.
Well, I told you before, Minecraft isn't worth the billions of dollars Microsoft paid for it.
Yeah, Microsoft is kind of screwed right now because they spent too much money for it. Now they're trying to get as much money as they possibly can, and it's not really. It's kind of ruined it. Like, no one's gonna play it anymore. Besides, like, little kids.
Well, I don't think, honestly, any game is worth the millions of dollars they've put into it, because games devalue over time. A game comes out for $60. If you can wait 3 or 4 years, it drops down in price to, like, say, $10, $5, $2, depending on a Steam sale.
Yeah, and look at Mass Effect, where they spent millions of dollars on that game, and the facial animations look like, I don't know, like some guy who's having a seizure.
The facial animations look like crap because, you know, they hire animators that aren't worth the money because they just have money to spend. And it's all the shareholders at the end of the day who make or break whether or not a company keeps pushing this much money.
Yeah. It's pretty sad. I mean, I can. Oh, let me see. I got someone watching me right now. So yeah. Anyways, I gotta start working on this. Thanks for talking, Jeff.
Yeah.
So yeah, I'm going to start coding this thing. I'm restarting my train engine again because I feel like I could do it better. I was just messing around with it last night and I cannot get this stupid thing to work. It's just here. I'll show you what it's doing. I'm gonna load it. It's just driving me up a wall because I tried running this thing and it looks like spaghetti. And I cannot figure out why. So I'm just going to restart. Sometimes when I restart, it just automatically works. Yeah, so if you look at this thing, it loaded almost instantly, which is amazing for how many, because this terrain is like over 33 million vertices on it. So it loaded almost instantly. So I did a good job optimizing it. However, it's not terrain. It's like, I don't know what to call this. It's like a bunch of spaghetti strings. And if I look underneath, it looks different. Yeah, there's something seriously wrong with this. And I worked on this for literally 3 hours yesterday and I couldn't figure out why it's doing this. So, I mean, if you look, the chunks are just little strips. And they even like have like little bands on them. It looks like a hazard sign or something. It's really bizarre. And then if you go over to these chunks, have like, if you look underneath them, they look different than the others. They have like these long bands. It's really weird. I've never seen anything like this, and I don't know how to fix it. So I'm just gonna restart. Of course, if you look at system, and triangle and axis are out of bounds. And I don't know why that's happening, because it shouldn't be happening. I mean, I could just stick with this, keep working on this more, but the problem is, well, I've been working on this for like 6 hours and it hasn't looked any different. I'm kind of tired of it. I want to do something new, so I'm going to restart. Maybe as I'm working along, I'll figure out how I messed up. So I'm going to close this now. That project's done. I'm not going back to that again. I'm now going to restart. So this is going to be like my, I don't even know what attempt this is. I'm just going to go terrain engine. And let's just go 5. I'm going to say it's the 5th attempt. I don't even know. So I'm going to go create program. Create project. Sorry. Okay, I'm going to close this. And then I'm going to go to project. And I'm going to go ahead and go create new folder. This folder is going to be resources. And we'll create a new folder. This is going to be scripts. And in my resources, I need to create an image folder. I need to create so I have images. Then I need the shaders. Excuse me. I finally need the dog is screaming upstairs. I don't know what's going on. Okay. Finally, I need. What else? So I got images. I got shaders. I got scripts. I also need prefab. That's what I was looking for. And I spelled it weird. Why did I put an E before the A? That's weird. Okay, so I got prefab, shaders, images. So I'm going to go to images, and I'm just going to load up the images. I'm doing exactly the same thing I did yesterday. It's kind of weird, but I'm just restarting. So if I look at it again, I might figure out what I did wrong. Because this is really weird programming I'm doing. I've never done anything like this before, and so I gotta do it in a funny way, I guess. So I figure out how to do it. I'm trying to get my mind to wrap around how this works. So maybe restarting and doing it all over again will get me to think about it more, and maybe I'll figure out what was wrong last time. So I'm gonna go like that. I need maps and I need super high quality, and I'm going to apply. If this load, while it's loading, I'll just show you the map. So this is the actual. Oh crap! It's freezing. That was weird. So this is the actual map I'm trying to build. This is it, I think. No, that's an early version of it. That's an early version of it that I'm not using anymore. It's pretty cool looking, but that's not it. This is the one I'm using. It's a lot higher quality. It's twice as many pixels on it. It takes a lot longer to load, but it's very nice. As you can see, I can zoom in all the way as far as it will let me, and still doesn't look pixelated at all. Very high quality image, and you can see it has like mountains and stuff. They're kind of branching out and stuff. It looks really pretty when I fully render it, but I gotta render it first where you can see it. So I'm gonna go here. It was actually originally made for CK2, but I'm using it to make my own thing now because why not? So I'm gonna go here, and I'm going to go drag this down. This is gonna be 28192. This is going to be high quality. And I'm going to apply. I think that's good. Yes, that's good. Such a pretty map. I love the colors, the green and all that. It looks so much like a real world. I put a lot of effort into making that look nice. Wondering how I made this map. I use a tool called CK2 Generator. I didn't actually use the tool to build the map itself. I built the map itself using a program called GIMP. I use GIMP to, you know, I took textures that are used by the CK2 generator and I cloned them on. I kind of mixed and matched them and shaped it out to make the shape. I can actually show you the file where I made it. I believe it's right here on my desktop somewhere. Where is it? Untitled XCF right here. So the the textures I use to make this are actually from here. It's a generator program for generating maps for CK2, and it happens to have these wonderful textures that come with it that it uses to generate the maps. And I just borrow these because they're open domain, public domain. So I just borrow these little pictures, and I use them to paint the whole texture for the map. So I just took those pictures, and I cloned them, and yeah, this is the height map. But if I hide the height map, hide the normal map, hide the heights, then I need to show the desert layer and the mountains. See, there's the map right there, and I can put the ocean in the background. There's the map. See, it's still just a bunch of layers in GIMP. So the reason I did it in layers is so that I can edit one layer. Like, I feel like changing the mountains later. I could just change this layer on its own. I don't have to worry about messing around with the desert or the grass, because they're all in their separate layers. It's a very powerful way to make images. I'm actually thinking about changing the mountains, because right here the mountains are a little too thick. I might want to change that. Anyways, yeah, and there's also even snow. I didn't use this by default, but this snow I can put in the mountain peaks. You can really see the shape of the mountains there. You kind of see how they're kind of bundled up together over on the side. It's kind of weird looking. Yeah, but see what the mountains are. There's mountains here, there's mountains there. Nice little ranges I formed. This range is cool, like ranges over. Yeah. So how I made this was I just started with a land mask, which is this shape. I built a basic shape. I just painted it of what I want the land to look like. And if you notice, there's like all these weird like little crevices and stuff up here. Those are actually just little random. I made randomized shapes, and I just deleted little crevices because I wanted this to look like the north, like Sweden. And Sweden has a lot of lakes, and it has a lot of what are called fjords on the northern coast of Sweden. So I simulated that by just putting a bunch of random shapes. And yeah, it looks pretty nice. I really like how this shape looked. And then I just took the shape and I painted this on it and this on it. So yeah, I took this and then I just changed it to the shape of the shape. And then I added an ocean to the background. And then I painted on the desert on the south. And I added the mountains. The mountains I actually started with just this, which is just a bunch of, if you look really closely at this, they're just a bunch of straight lines that show where the mountains go. And then I selected the mountains and I fanned the selection so that it got like towards the edges of it would be softer, and then I just filled it in with the mountain background. And it looked like this after it's done. See, it looked like that, so I get rid of this. And it just looks like this. It doesn't look like that shape anymore. But it's a lot blurrier, but it looks really nice on the map. It doesn't look like it has sharp edges on the edges of the mountains, which is what I wanted. So it worked pretty well, and then I put these together. Of course, I made sure that the mountains have a clipping so that they don't go over the water. That was one thing I had to make sure of when I was making the mountains. So the mountains end abruptly when they hit the water. that's how I made this map. So it looks very pretty. Anyways, I'm going back to the Unity project. And my color map has already been imported. It's been imported for a while. So I'm going to go ahead and go back to the desktop. And I don't know why these windows are here, because I closed GIMP, so they shouldn't be here. Yeah. Okay, and I'm going to go ahead and grab the height map, drag it in. So there's 3 maps I made. There's a normal map, which I just literally made by plugging the map into a normal map program, and it just spit this out. I didn't even do any effort to make this. This one I made by hand. It just has random noise on the terrain, so it looks a little hilly, and I put white gradients going to transparent on the mountains, so the mountains look like they're really tall compared to the land, and it looks really pretty. And of course, the water level is actually 97, which is the same as it is in CK2. Yeah, because this is originally for a CK2 map, but I'm changing what I'm doing with it. So I'm going to go here, and I'm going to go ahead and make this be 8192 and apply. Actually, I need to do some more changes to this. This needs to be high quality, and it needs to not have bitmaps. It needs to be point, because I'm not actually rendering this image. This image is just used to build the bitmaps. I mean, used to build the actual terrain heights. So I want it to be as high quality as possible. Since I'm not actually rendering it, oh crap, I need to make read and write enabled too. Okay, I'll just wait for the finish loading. But since I'm not actually rendering this image, I don't need to worry about like making it so it's not pixelated looking, or making it so it renders faster with bitmaps. I don't have to worry about any of that, because this image is not going to be actually used to render. It's just used to build the heights of the terrain. So what I'm going to do is I'm actually going to go through every single pixel. If you remember yesterday what I did, you go through every single pixel of the terrain, pixel by pixel, and you determine how black and how white that pixel is. And the whiter the pixel is, the higher the terrain is at that pixel. So, I mean, this is an 8192 by 4096 image. So if I type this in, 8192 times 4096, you'll see this has 33,554,432 pixels. That's a lot of pixels. And if I had to go through every single pixel in this image and determine the height at that pixel, it's going to take a really long time. So there are many ways I can make this be faster. The first way is I can use what I call MIP level. So you'll see me do this. I make a number that is divisible into 8192 and 4096. So basically a factor of 2, a power of 2 number. And this power of 2 number will be divided, will be the amount of pixels I skip. So I skip 4 pixels, I grab a pixel, skip 4 pixels, grab a pixel. If the MIP level is 20, then I skip 20 pixels, I grab a pixel, skip 20 pixels, I grab another pixel. However, it has to be a power of 2, so I can't use 20. I could use 32, 16, I could use 8, 4, 2. It has to be a power of 2 so that it always evenly goes into the map size, because the map size is always a power of 2. And of course I'm going to have checks to make sure that these numbers are always powers of 2, and if they're not, it's going to throw an exception, so you cannot render the map, because it might run into an issue if they're not powers of 2. It potentially could. It might not, but I just don't want to worry about that. So if this ever becomes an actual game and someone tries adding a texture to the game by modding it, and the texture happens to not be power of 2, it will throw an error, because it's not possible. Because the MIP levels might not be compatible with that number. Yeah, so I gotta use a MIP level. That's one way in how I can make it render faster, is simply by skipping pixels. It makes the map less detailed, but really you don't need 33 million pixels to have a detailed map. You don't need that many. You don't need 33 million vertices on the map. That's kind of ridiculous. So I'm not too worried about getting rid of some of that detail. Another way in how you can make the map more detailed, make the map render faster, is what I was doing yesterday. Use the graphics card, because the graphics card is a lot different than the CPU. So the graphics processing unit, the GPU, can handle more stuff at the same time. So think about it like this. The graphics card can always render things on your screen. It's always rendering stuff constantly. It's always running this image, this massive image that covers your entire screen. And depending on the size of your monitor, that massive image can be millions of pixels. Like this monitor I have right here is kind of a funny size. I think it's like, yeah, you can't see the whole monitor because my monitor is such a weird size I can't film the whole thing. I'm going to move it around a little bit so you can see. My monitor is really weird. It's like a double monitor in one. But, actually I don't know what size it is. I think it's like 2048 or something strange. Yeah, mine is 2560 by 1080, which is really weird. But anyways, if you look at 2560 by 1080, if this ever wants to load, why is this not loading? Oh, man, it loads right before I close it. Okay, if we look at 2560 times 1080, that's 2,764,800 pixels. And if you think about that, that's kind of crazy, because every single frame, every single time there has to be an update on the screen, it has to go through all 2,764,800 pixels. And look how fast I can move my mouse, and there's absolutely no lag. Now, if that was running on a central processing unit, if that was running on the CPU, there would be a hell of a lot of lag, because the CPU is designed for doing one thing at a time. So it would literally have to go pixel by pixel by pixel by pixel all the way across the screen, row by row, column by column, until it rendered the entire image. And that would take, I mean, it wouldn't take forever. It would probably take a few milliseconds. However, if there was it would be a lot longer than it does now, and you would actually notice like frame drops when I move my mouse around and stuff. And that would basically make computers be not as powerful as they are now. They would not be able to do as much as they can do now. They would be pretty much useless for video games. They would be basically confined to only really simple business applications. Like computers would not be as cool as they are now. So thankfully, people came up with a new type of processing unit called the GPU. Unlike the CPU, the GPU, and the graphics processing unit, handles multiple things at the same time. So the CPU just goes pixel by pixel by pixel, and the GPU does the pixels in chunks. Now, the GPU has issues with it too, because it does it, when it does everything together in a chunk, it actually has to do the same thing for all the different things it's doing. So there can't be branching things like if statements, but still, it can do a lot more at the same time. I mean, there can be if statements under certain conditions, but you really have to be careful how you use them. Branching code on a GPU is not good. So the GPU has its issues, but it also has its benefits, which are very, very good for graphics, because they allow you to calculate the colors of a million pixels in less than half a millisecond. Because it does it in clumps, it does it so fast. So if I go back to Unity, and I'm just going to go to my resources and shaders, and I'm gonna make a shader. So what is a shader? Well, you may be used to coding stuff on the graphics card already. I don't know if you are or not, but I mean, I assume that if you're watching this video, you have coded on the CPU before. You have used C# to code things before. And when you code with C#, you're basically coding on the CPU. You're coding on the CPU. You're commanding the CPU to do things. That is what most programmers do, is they just strictly stay with the CPU, and yeah, that's all they do. But what I'm going to do is I'm going to code special programs that are designed for talking to the GPU. And these programs are actually built on the CPU. They're packed together in a little package called a buffer. And the buffer is sent over wires into the GPU, which this takes a little bit of time, but it's really minimal. But if you are sending a lot of buffers, I mean, there's one thing you want to be careful for. You don't want to, when the CPU is talking to the GPU, you don't want to send a bunch of little buffers, because that would slow things down. You want to send everything in a big buffer, a single buffer, because the smaller amount of buffers, the faster the communication is, the faster the processing will be. So I want to put everything together in a giant buffer, and I'm going to send this buffer to the CPU, the GPU from the CPU, and the GPU is going to read this buffer, and then it is going to compute stuff using commands specified in a shader, which is a special program for the GPU. And then after it follows the commands in the shader, it will send it back to the CPU, and the CPU is going to pull the buffer apart, and it's going to use the data to build the terrain. So what I'm describing right now is a special kind of shader. Most shaders, the CPU just sends stuff to the GPU, and the GPU sends information directly to the monitor of the computer. But this shader I'm talking about right now, the CPU sends data to the GPU calculates the data, and then it sends it back to the CPU. This is something that doesn't usually happen in shaders. It's something that's completely new, because GPU up until now, it hasn't been able to send things back to the CPU. All the GPU does is it calculates things and it draws on the screen. That's all it's done in the past. But in DirectX 11, graphics cards are now capable of sending information back to the CPU. So this means you can calculate things using the power of a graphics card that don't necessarily have to do with graphics. You can just, for instance, you can just go to YouTube. You can just go to YouTube. You can minimize this video. You can open a new tab. But what you can do is you can go to YouTube and you can type in GPU powered, and you'll see a bunch of new things that are coming up. This is a relatively new technology where you can have a GPU powered pathfinding system or a GPU powered physics engine, and they're extremely powerful. There's a particle system I saw in one video that's GPU powered that has over billions of particles on the screen, and it literally runs with no lag at all. And then they tried doing the same thing with a CPU powered particle system, and the frame rate was 3 FPS. I mean, it's amazing how much more powerful a GPU is at certain things. At certain things, mind you, but it's more powerful at those things. So you can use. So what they did was they actually the CPU sent information about the particles to the GPU. The GPU calculated the positions of the particles for the CPU, and it calculated all the collision information and the directions the particles should be going and all this stuff, and then it sends that information back to the CPU in a giant buffer, and then the CPU then just simply draws it on the puts the particles together, and then it actually sends it back to the GPU to be drawn on the screen. But yeah, this sort of thing was not possible before, because the GPU just drew things on the screen, and it wasn't capable of doing branching. It's not capable of doing branching logic with if statements. So that sort of thing wasn't possible before, because you couldn't send things back to the CPU from the GPU. But now you can. And how you send things, when you build a shader that can take stuff from the CPU, and then the shader sends things back to the CPU when it's done, this is called a compute shader. So I'm going to go ahead and make a new folder, and this folder is going to be called compute shaders. And I'm just going to create shader, compute shader, and I'm going to call this map calculator. That's what it's going to be for. So a compute shader is actually a special file in Unity. Actually, shaders usually don't have file types, which is really interesting. In Unity, they have a .compute file type, as you can see here, but shaders by default don't have a file type associated with them. Unity just has it, so it makes it easier for you to recognize them in Unity. But most shaders are actually just strings that you store in memory. So you can actually like if you're just coding raw OpenGL or raw DirectX, if you're not using a game engine like Unity, when you're making a shader, you could just type it out as a string, store it in a variable, and then send that variable to the graphics card. And that would be like sending a shader command to the graphics card. So there's actually is no file type. It's actually just, if I look at this file type, if I go show and explore, and I look at this file type, it's just text. There's no compiled binary or anything. It's just a bunch of text. So it's really just a text file with a different thing. Because all the computer does is it takes that as a string and then it sends it to the graphics card. It doesn't have to compile it. Which is really interesting. So I got a phone call. Give me one moment and I'll be right back. Very sorry for that. That was kind of annoying, but okay. Let's see if I lost anybody because of that phone call. No, I did not. So someone who's been watching my streams lately. I really appreciate it. I feel like I'm not talking to no one when I'm ranting on about stupid things like DirectX and shaders, but it's pretty good. Someone's listening to me. Okay. I'd like to know who it is who's watching. So if you could comment, that'd be awesome. Just type something in the chat. So I could know, that'd be cool. Who you are. I'm just loading up the goofy thing. Wait, it says one person's watching. Is that me who's watching? That'd be really funny if it is. There's actually no one watching, I just think there is. Okay, so alright, so this is a compute shader. Compute shaders are kind of funny because they don't look like a normal shader. Have you seen, I'll show you what a normal shader looks like. Like this is just a normal this is a normal compute shader. I mean, this is a normal fragment shader and a vertex shader put together. So a vertex shader is for so most shaders, what they have done in the past is they actually are plugged into what's called the graphics pipeline, which is just a series of steps that you go through to draw stuff on the screen. So if I go to learnopengl.com, I open TeamSpeak for some reason. I'm closing this. I go to learnopengl.com and I go to Getting Started OpenGL. No, it's creating a window maybe. It's a chart I'm looking for. Hello window. Where's that chart? Oh, triangle. There we go. So this is the secret to shaders. This is how they work. There's something called the graphics pipeline. It's usually a lot larger than this, but this chart is a basic example of the graphics pipeline. So first you take your data. The CPU gathers all the data about where the vertices for every single thing in the mesh are going to be, and where the triangles are, and how to make the triangles, and all that stuff. And then it sends it to the GPU. That's what this arrow is. This is where it sends it to the GPU. And when it gets sent to the GPU, the first thing it does is called the vertex shader, where it maps out where all the points are on the screen. And this is actually a shader, meaning you can code this part. So you can change how this part works by coding a shader for it. And then it goes to the shape assembly, where it draws lines between the different points. This is a part you cannot code. There's no shader for this part. It just does it automatically. And then there's the geometry shader, where it makes some alterations between different points, and you can do crazy stuff like changing the shapes. And this is a part you can code yourself. Then it goes down to rasterization. So it's finished designing the shapes, and now it's going to start making pixels to map out where the shapes are on the screen. So it maps out different pixels to different parts of a shape. And this part's done automatically. Then it goes fragment shader. The fragment shader is where it takes these pixels and it colors them, depending on where they are on the shape, what texture, and what texture coordinate that part of the shape has. Yeah, and this part can be coded by you. You can code the fragment shader. And then it goes to test and blending, where it mixes shapes together, puts shapes in front of other shapes, handles transparency of shapes, all sorts of stuff like that. And that's the final step, and you cannot code that yourself. That's done automatically. So that is the basic graphics pipeline. Usually graphics pipelines actually have a lot more steps to them. Like I can go Doom, graphics pipeline. If you look at a game called Doom, the latest Doom, you can see this is the graphics pipeline for Doom. So this is the first step of the graphics pipeline for Doom. Then it goes to this step, and it does this thing, and then it does this thing. So Doom actually has over 60 steps in this graphics pipeline, so it's a little more complicated than that, but you kind of get the idea. That's very pretty looking. Okay, yeah, so you can kind of see how it works. Sorry, I was just looking at that. It's kind of cool. I was curious, because the depth of field gets a lot of quality from the thing. And yeah, I was talking about Minecraft earlier, because it's kind of sad what happened to that game. Anyways. Yeah, so this is the fragment and the vertex shader. As you saw in that pipeline, these are the parts you can code yourself. There's also geometry, which is not in this shader, but this shader handles the graphics on the vertex parts of the shader. This is a compute shader, which is completely separate from the graphics pipeline. It allows you to code stuff, to compute stuff, and then send it back to the CPU, for the CPU to do stuff with it. So this is a completely new type of shader, introduced in DirectX 11, that is not on the graphics pipeline. So I'm going to start coding this. I'm going to start coding this shader, and I'm going to make this shader do some stuff to build the mesh. So what this shader is going to do, I need to make a list of what I want the shader to do. I already built this yesterday, but I'm just going to restart building it today, like I said. So I want this shader, oh, there's a copy of it right here, but I want this shader to do a few things. So So what I want the shader to do is it's going to take in inputs. Height map. So it's going to take in the height map image. The height map image is going to be passed into the shader. Because shaders are very good for handling images, since they are multi-threaded, since they can handle multiple things at the same time. They can go through an image in a breeze because they can handle multiple pixels at the same time. So they do the pixels in clunks of pixels instead of one pixel at a time, basically. So they take in the height map image, and then I also want to take in. I want to take in a value that's going to represent the amount of space between every single vertex of the image. So I'm going to call this grid size, which is amount of space in the final mesh, amount of space between every vertex and final mesh. And I also want to pass in the MIP level of the mesh. So if you remember what I talked about earlier, one way and how I can speed this up is I can make the mesh have less detail by skipping pixels by using only every 4 pixels instead of using every pixel of the mesh. Skipping every 4 pixels. So the map is less detailed when it's done, but it makes it less strenuous in the computer because there's not as many vertices and it doesn't have to calculate as many things. So I'm going to add a MIP level, which is amount of pixels to skip every pixel calculated. Okay. Then, so I have input, processing, output. This is actually the 3 steps of any program, even on the CPUs: input, processing, output. So it's going to input all this stuff. And then I'm going to process these inputs. The height map I'm going to build. Look at every pixel of height map. Oh yeah, and I also want height scale. Sorry, I forgot this. Height scale. And the height scale is going to be the maximum height of the map. So the height scale is basically, I want the height to be from 0 to 3 on Unity units. That's the height of the map. It's going to be anywhere between those units. And it'll scale the map to 3. So this will be the maximum height of the final map. Look at every pixel of the height map. Determine the brightness of the pixel and use this value to determine the pixel of the height map within the MIP level, right? Determine the brightness of the pixel and use this value to determine. My dog is howling. 1 second. So I'm going to look at every pixel of the height map, determine the brightness of the pixel, and use this value to determine the height of each vertex of the mesh. Take height scale into account. Okay. So I'm going to do that, and then I'm going to build a vertex, a vector 3 for every pixel that will represent that will represent a vertice of the mesh. Each vertice text position of the mesh, the final mesh. So I'm going to determine where each vertice of the mesh is going to be in the shader. So I don't have to do this on the CPU. Because you know it's going to be like 33 million vertices. And if I do this on the CPU, it would take forever. GPU could do it really quick. So I'm going to do it on the GPU. Then I'm going to build triangles. Build an int array of triangle positions that will be used to triangulate the mesh. So how is this going to work? I'm building an int array of triangle positions that will be used to triangulate the mesh. Well, I'm going to open Blender for a second. I think that's the best way to visualize what I'm talking about. Blender is a 3D modeling application. I love Blender, it's very fun to use. But I'm just going to go add mesh, and I'm going to add a plane. So we're going to look at this plane really closely. If you look, it's just a square. I'm going to triangulate it, because everything in Unity is made up of triangles. So I just triangulated that really quick. This would actually render in Unity pretty well. This is just a flat plane made up of two triangles. And if you look, 3D meshes are made up of multiple components. There are multiple things that work together to make a 3D mesh. And this is all graphics programs use these. So even stuff drawn on your desktop are actually drawn in 3D with 3D meshes. But you don't really see that because it's all flat and it's an orthographic view, so you don't really see it. But yes, that's how the computer draws everything nowadays, is with 3D meshes. So if you look at this, mesh is first made up of 4 points. These are the vertices. And these vertices are connected with, if I just delete the faces, all that's left are the edges and the vertices. So I'm going to delete the faces. Only faces. So now that's left, you can see, is the edges of the mesh. So from the vertices, so we start with this. Here, I'm going to actually make it so you can see this better. So we start with just the vertices. Just the vertices. I guess you can't have just vertices. Yeah, you can't have just vertices in Blender. But okay, so we start with just the vertices. So imagine the edges are gone and we just have the points that are in the corners. These 4 points. And that's the first thing we do. We're actually making a giant grid of these. That's the first thing we want the shader to do, is compute where all those positions can be. So they can be higher, they can be lower, depending on where the height map is. That pixel of that corresponds to that vertex on the height map. And the next thing we have to do is we have to build edges that connect these vertices. And that is where the triangle array comes in. So if you notice, every single triangle has 3 vertices connected to it. And also, there's actually a long array of vertices. That's how vertices are stored in memory, is a long array. And so every single vertice has an index in that array. So let's say this is 0, this is 1, this is 2, and this is 3. Those are the indexes of all these vertices in the array for this mesh. And the triangle simply lists the order that you use those indexes to build the triangles. So every 3 indices in the triangles array represents 1 triangle. So the triangles array might look like this. Let's make this so I can see things better. Okay, so remember, this is 0, 1, 2, 3, right? And so the triangles array, for the first triangle, I want to build a triangle out of these 3 points. I want to build a triangle out of those 3 points. So how do I do that? Well, let's start with this point. So this is point 0. So in the triangle array, we are going to add 0. That's the first int in the triangle array. Then we're going to go 0, 1, 2, 3. So now we're going to go to the third point. So let's go 3. And then the next point in the triangle array of int is going to be 2, because it goes to the second point. And then that's one triangle, because every 3 indices in the triangle array represents one triangle. Then we're going to go to the next 3 indices in the triangle array. We're going to start here again. So we're going to start at 0. Then we're going to go to 1, which is this one. And then finally we're going to go to 3, which is this one. So the next 3 correspond to the next triangle. And they explain how to build the next triangle using the next 3 indices. Now if you notice, when I was doing this, I was always going clockwise. Wherever I start, I always go clockwise to the next vertex. If I start here, I go here, here, here. If I start here, I go here, then here. If I start here, I go here, then here. So when you always have to go clockwise when you're building the triangles, because if you build them counterclockwise, it will actually, when you render the mesh, it will actually be upside down. So this is very important. You have to make sure the triangles are in the triangles array clockwise. That's pretty simple. So this is literally an array of ints, an array of integers, and this array of integers would be the triangle array for this thing. So I have to build an array of integers that look like this for the massive mesh that has like over 16,000 vertices. But I have to do this and say give the positions of all the vertices in a proper order, and that will be my triangle array. So for every single vertice, this is one rule we should understand. For every single vertice in the mesh, there are six triangle points, because there are 2 triangles. So for this vertice, there are 6 triangle points. There are 6 indices in the triangle array, because it's this, 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 and this, this, this. Then if I go to this vertice, let's just like, this is kind of goofy. Okay, so for this vertice, there are 6 more. 1, 2, 3, 4, 5, 6. And then if I want to go up to this vertice, there's 6 more. There's another square right here. And then there's another square right here. And then for this one, there's another square right here. You see what I'm saying? So the size of the triangle array is going to be the size of the vertices array times 6. However, there is a problem. There is a problem with this. What if I get to the top or the right side of the mesh? Well, when you get to the top or right side of the mesh, there's not going to be anything after that, right? So imagine this is the top of the entire grid. There are no triangles above this. There's no vertices above this. So there aren't actually six triangle array positions for this vertice, because we're at the top and there's no triangles above this. So the equation to get the length of the triangle array from the length of the vertices array would be like this. You go triangles dot length, this is your pseudocode, equals vertices dot width minus 1 times vertices dot height minus 1. I'll write these are on these. Lower operations, that's kind of important. So So if you think about it, you have to subtract 1 because you can't have... Oh yeah, and then you need to multiply times 6. Times 6. Because there's 6 indices in the triangle array because there's 2 triangles for every single point. Because it makes a square to the upper right of every single point in the vertex array. So what we do minus 1 because there's no square to the upper right of stuff on the edges. So we just get rid of the edges and we just subtract 1 from the width and the height. So that's how you get the size of the triangle array from the size of the vertex array. And that's how the triangle array works. And you think that that's just how I'm going to build on the compute shader. However, that's actually how it works on the CPU as well. So once we're done with the compute shader, we don't have to do any more work with it. Because if I go back to the CPU, let's just pretend this is a C# program. And I want to make a mesh, I can just go mesh equals new mesh. And I can take the array that looks like this, that I built on the graphics card, and I can just go triangles, mesh.triangles, equals the array. This is just pseudocode. But I can just take the array of ints that I made, and I can just go mesh.triangles equals the array. I can go mesh.vertices equals the array of vertices. Right? I could do all that. And the mesh will literally be built. That's all I have to do. So if you want to make a procedural mesh, all you have to do is you have to make the list of vertices, you have to make the list of the triangle positions in the vertices, and then you have a mesh. Assign those to a mesh, and then the mesh will automatically be built. So that's all you gotta do. That's all a mesh is. It's just, in data, that's all a mesh is. It's just a bunch of vertice information and information about how those vertices are connected to make triangles. That's literally everything you need to know about making meshes. So, and that's what I'm doing, because I'm making a map, and I need to make procedural meshes. I could use the default Unity terrain, which this is actually how the default Unity terrain works deep down. But I'd rather make it all myself so I have more customizability over it, more power over how it works. So, okay, back to the shader. Your mind's probably blown from all the information. You're probably either confused or you're really learning a lot right now. It really depends on if you get it or not. That's how most things in programming are. You either get it or you're completely confused. That's sadly how it is. I go to school every day and I see people are completely confused, and yet I can understand everything, and I feel like, why me? But I mean, I am thankful though that I understand these sorts of things really easily. So we build the interarray triangle positions that we use to triangulate the mesh. And then I think we should do one more thing. We need to build the UV map of the mesh. Which is used for texturing the mesh. So this is the final thing we're going to do on this shader, this compute shader. So this compute shader is going to build 3 things basically. It's going to build the vector 3 array for the vertices. It's going to build the interarray of the triangle positions in those vertices. Every 3 indices of this triangle array will be 1 triangle. And then we're going to have a UV map of the mesh, which is used for the texturing. Now, if you don't know what a UV map is, I'm going to explain that really quick. This is something that's really simple. A lot of people know this. But if you don't, just in case you don't, I'm going to explain it. So, I'm back in Blender, because this is the best way I can explain how a UV map works. I can actually make a UV map in Blender. Well, let's think about this first. I have this cube, And let's say I want to texture this cube with, let's go to textures.com. Let's grab our textures really. That's not what I want. Crate. You make a crate texture. Yeah, there's a few. I want like a good tileable one. Let's see. Most of these are kind of like they have stuff on the edges. Let's just go plank. Let's go plank texture. Yeah, like this. These are pretty. Let's grab this texture. I'm just gonna grab this. I'm gonna go like really small because I don't need that much. Okay. I love this website. This website is wonderful for game textures because they're super high quality and they're free. You can only do 15 per day, but still it's pretty nice. And you can also buy more if you want to. But the 15 free per day is just wonderful. So I got this in my downloads now. Okay, I'm gonna go into here and I'm gonna actually go to materials. This is just a Blender thing I have to do really quick so I can see the texture on the thing. I gotta go here and get rid of specular of this material so it's not shiny. Then I go here, and then I gotta go texture this material. Wait, what is going on? I gotta assign it. Okay. I don't know what's going on. Okay, so I got this, and why is this looking weird? What is going on? I'm sorry, I gotta figure out what this thing is doing. So I'm gonna go to edit mode, delete. I'm gonna add mesh cube. I'm gonna go to delete. I'm gonna go to shift S and selection to center. First to center, and then shift A cube. There we go. So center. Then I'm going to go materials, I'm going to go new material, and this material is going to be called planks. And I'm going to make this like this. So this is just that for adding a texture to a thing, you have to make material, then you have to go new. There we go. Then I go open. I'm going to go to my downloads. I can grab, I'm going to grab this texture. Okay, so now I just textured this thing. However, you can't really see it because I got to go to here and go material mode, and then I gotta actually add a lamp. I'm sorry. I will explain stuff in a second. I just gotta set this up first. Okay. So there we go. I just textured this cube with the wood texture. However, if you look at this, does that look like a wood texture to you? No, it doesn't. Because this texture doesn't know how to map out this texture to this cube. What I have to do is for every single vertice of this mesh, I need to make a value, a UV value, that says what coordinate I'm drawing the texture from for that vertice. This value is between 0 and 1. So I'm just going to go to UV editing. So you can see the UV map. Now if I go here, I go like this. This. Okay. I need to make it so this is not like transparent like that. Like that. Okay. And then I got to go here, material. Sorry, technical difficulties. Okay. Okay, if I just go rendered, you can see it. So it's actually is drawing the texture on there pretty well by default, but it's not how I want it. I want to map it out. I want to map the texture out so it actually does it properly. So how do I do this? I'm going to go back to material. I'm just going to go U, unwrap. look at that. The texture all of a sudden is mapped out perfectly to the mesh. Now what did that just do? This is what I need to do procedurally in the code. Exactly what this just did. So I need to look at every single vertex of the mesh, and I need to assign it two values, a vector 2, where each vector is between 0 and 1. 0 being the upper left corner and 1 being the bottom right corner. And if I view the actual image in this thing, it'll make more sense. Okay, so if I select everything, you can see, let's just select this one face. So this is the UV map for this one face. And if I go here and I click this, I can move it around and it distorts that part of the mesh. It's not neat. So I can distort the mesh around that corner by just grabbing the corner and moving the corner around. See how it distorts it. But how I want it to be is perfect ones. So this is UV0, this is U0V1, this is U1's V1, and this is U0V1. So the UV actually stands for the two different coordinates in the UV map. UV doesn't actually stand for something. UV stands for the two coordinates in mapping a texture. So I map the texture out to between 0 and 1, and I can use that to map out the texture. I can even make this value be larger than 1. But let's just grab all these and scale it up. No, how do we do this? I'm going to scale it to be 2. So now everything, remember this is 0, 0, and this is 1, 1. So everything is like wider than the UV map. And what is that doing? It simply makes it so the texture tiles outside. You see the texture is now tiling. So that the default texture is in the center and it's just tiling like over the edges. And by Unity it doesn't tile by default, but you can have it do that. In Blender it tiles by default and there's nothing else you can do with it. But in other engines like Unity, you can make it so it clips, so that on the outside edges just doesn't add anything else. It just kind of continues the last pixel that's here, and it looks like a long band going across. But yeah, that's how you do it. So that's what we have to do procedurally. We have to map out every single vertex between 1 and 0 on the map, so we can draw the texture to it. 0 being the upper left corner of the texture, and 1, 1 being the bottom right corner of the texture. So if I go back to the default, let's make the map right now. So I'm just going to go ahead and make a plane, and I'm going to go GY. Actually, why is this not in the center? I'm going to go in here, delete this. I'm going to go add mesh plane, and I'm just going to make okay, I'm going to go cursor to center and add mesh plane. That's annoying. Okay, I'm going to scale this out, and I'm just going to do some tricks here. I'm going to add some loop cuts. And add 100 cuts. Imagine this is the map. So the map is going to be a giant grid of vertices, right? And every single element of the grid is just going to be a triangle. So this is, there we go, I did it. So this is what the map is basically like when it's fully rendered. Of course, it's going to have different heights. So the different vertices of the map are going to be higher and lower depending on where they are on the height map. So I can actually make like little mountains. Let's do this. Make like a mountain by raising all these, making like a nice little hill. Lower these, make it a little lake or something. Yeah, so there's like a little mountain range. I mean, this is kind of how the map is going to look when it's done. This is a really crappy example. But So I need to map out, let's say I want to map out this wood texture to the map so that the entire wood texture is only shown once across the entire map. How would I do that? Well, I need to map it so that the upper left corner of the UV map is 0, 0, and the bottom right corner of the UV map is 1, 1. And everything in between this, all these points between it, has to be scaled so that they're evenly spaced apart between those 2 points. So I can quickly do this just by going U and then unwrap. And if I go to UV editing, you can see it kind of distorted it a little bit because of the hills, but it basically did it. So if I go to default, add a new material, I'm going to call this material whatever, it doesn't matter. And I'm going to go new texture, and I'm going to open downloads this texture I added, the wood texture, and I'm actually going to view the texture. Okay, it's kind of shiny, it's hard to see. Get rid of the specular. But yeah, you can see now I mapped out this material to the entire map. And this is basically what I'm going to do. I'm going to map out the entire map texture to the entire map. Isn't that cool? You can see the dips in the wood and like holes and like, that's kind of cool looking, isn't it? But yeah, that's how it works. So if I look at it on the UV map, you see it's just the wood texture, and it has the different vertices that are mapped out to different positions on the texture. Okay, I've spent enough time with this. I think you understand what I'm trying to say. I think you understand how UV map works now. So I'm going to build a UV map of the mesh. So this is 3 things I'm going to do. I explain these really thoroughly. I'm going to build the vector 3 for every pixel that represent the vertex position of the final mesh. I'll build an array of triangle positions that will be used to triangulate the mesh, and I'll build the UV map of the mesh. 3 things I'm doing in the shader. Then output. Send outputs back to CPU. And back to the CPU, I'm going to send the array of vector 3s. I'm going to send the array of int triangle positions, and I'm going to send the array of UV texture coordinates. So I'm going to send these 3 things back to the send these 3 things back to the CPU, and the CPU will use this to then build the mesh, and then it'll send it back to the GPU as a built mesh to be rendered on the screen. All going to happen in the blink of an eye. And okay, I accidentally was editing the text file, so it changed the compute shader. Okay, whatever. I'll just go back. I'll Control Z that. And I don't want to lose this, so I'm not going to reload it. Okay. So, in fact, I'm going to copy this. I'm going to make a new random thing, close it, and close this. I'm not going to save that. Okay. So, let's go with this shader now. So shaders have what are called pragmas. A pragma is a command. A pragma is a definition. It's a pragmatic definition of what something is. So what this statement is doing here is saying I'm defining a kernel. A kernel is basically a function. It's basically a function in a compute shader. And I'm saying I'm defining a kernel called CS main. And so now the shader knows, okay, there's a function called CSMain here. I need to find it. And it goes down and like, oh, here it is. Here's CSMain. And then it builds this function together. And the graphics card prepares to use it, basically. Of course, I don't want to call it the CSMain. I'm going to call this CS Mesh Builder. Or Map Calculator. Map Calculator. Let's copy this and paste it here. So now it's gonna see that pragma. It's gonna be like, okay, let's build this mesh. Then we have our inputs and our outputs. These are all just variables that are right here. And I'm just gonna make this be a texture 2D because I don't want to write to this. I'm just gonna read it, and this is going to be the height map. Because you remember, if you look at the inputs, the first input I listed was the height map. Right? Height map image. And let's add some more inputs and outputs. So now I need to make the height scale, which is going to be the maximum height of the final map. This is going to be a float. So I'm just going to go uniform, float, and then go height scale. So this is a float that I'm going to pass into the shader. And this float is simply going to say the scale of the height map. And then I'm going to say uniform. So what is a uniform in shaders? I actually don't know. I know you have to say uniform every time you have a variable like this. What is a uniform in shaders? Oh, a uniform is like a parameter, basically. That's all that means. Uniform is a parameter. When you say uniform float, it basically builds that float as a class, as like an object class, and that way it can send it back and forth to the shader. Because if it's just sending a single float on its own, it can't do it. It needs to be packed in a uniform. It's kind of hard to explain, but yeah, that's what it means. I don't remember. So I'm going to go uniform float height scale, and I'm going to uniform float grid size, and uniform. Let's just make this be another float nip level. Okay, so those are the three main variables for calculating things. And of course, I also am going to need the size of the map. I'm going to need the x size and the y size of the map in pixels. I'm just going to store this together. Actually, I can go float2. I'm going to go float to dimensions. So what is a float to? A float to is actually a vector 2. So in shaders you say float 2, and Unity you say vector 2. They're the same thing. So I'm going to pass in a vector 2 that has the dimensions of the map, and I'm going to use that to calculate various things in the future. So it has the width and the height of the map in pixels. Of the height map in pixels. Yeah, that's pretty simple. And then I'm going to send in well, that's everything I'm sending in. Now what am I sending out? I'm going to send out a vector3 array of vertices, the triangle positions, and the UV texture coordinates. So the vertices are a bunch of vector 3s with the x, y, and z coordinates of every single vertice. So I'm actually going to go RW structured buffer float 3. And I'm going to say this is verts 3D. So what is an RW structured buffer? Well, if you remember, I talked about buffers. So whenever the CPU wants to talk to the graphics card, it sends things in a giant buffer. The fewer the buffers you send, the faster it runs, because it needs to spend less time computing everything. It's actually going to send everything over to the graphics card in a giant buffer when what I'm doing, but this giant buffer is made up of a bunch of smaller buffers. So, it's really complicated terms to describe all these things. I'm just making this very simple for you to understand. There are smaller buffers that it sends that are part of a larger buffer, And one of these smaller buffers as part of the larger buffer is going to contain all the vertices. And the structured buffer is basically a buffer to hold an array. So a RW structured buffer of float 3 is a read and write enabled array of vector 3s. That's all that is. I can read and write to it. And then I'm going to go RW structured buffer float 2, and this is going to be my UV positions, my UV coordinates. I could just go UV2D, UV2D. Okay, so that's for the texture information, which I just explained. And it's a vector 2 because it has a U and a V coordinate. And finally, I'm going to have the triangle information, which is RW structured buffer. Int is going to be triangles. Okay, I'm going to add comments after everything explained there. I'm going to get rid of this default comment because it's not really making sense anymore. And I'm just going to go to here, and this is, I'm going to put some comments. So this pragma kernel means this is basically a prototype. If you know what C++ is, you know what a prototype. If you don't, a prototype is basically just a little line of code that tells the program to look for something. It tells the program that something exists later on and you need to put it together. And this is telling you that there is a function called CSMap calculator later on and I need to put it together. So this is the prototype for CSMap calculator function. Then height map. This is the image of, this is the grayscale height map image that shows heights of different positions. Height scale is the maximum height possible. And the minimum is always 0. Make things easy. The grid scale is the size, the amount of space between each grid position. The MIP level is the amount of pixels to skip for every pixel calculated over the height map. The dimensions is the width and the height of the height map in pixels. The width of the and height of the height map in pixels. Vert2D is an array to hold vertex information x, y, and z values of each vertex. This is an array to hold the triangle information. Every 3 indices is a single triangle. And finally, an array to hold the texture coordinate information. Okay, so I got all my variables together. How many are there? There is 1, 2, 3, 4, 5, 6, 7, 8. 8 is the maximum amount you can have. So thankfully, I didn't go over that. This is perfect. I actually was trying to not go above 8 because that's why I put dimensions together in a single value. And what I could actually do is I could take the height scale, grid scale, and MIP level and put these together into a single value as well. Let's do that. So I'm going to go float 3. I'm gonna put these together into a single value by making a float 3, and this is going to be a float 3 of I'm gonna call this size data. This is going to be x is the height scale for the maximum height possible. Y is the grid scale, or the size between each grid position, the space. Z is the MIP level, or the space, or the amount of pixel skip. The amount of pixels skipped for each pixel calculated. This is kind of a long comment. That's okay. If I have it like this, you can see the whole thing. That's fine. And I'm just going to get rid of these 3 variables. So now, instead of 8, I have only 1, 2, 3, 4, 5, 6. I only have 6 things I'm setting off for, which is pretty nice. Very nice indeed. Yeah, I gotta use the restroom. I will be right back. Thank you for watching. Just give me one moment. Hello everybody, I've returned. I apologize for that little break. I mean, I've been going non-stop for quite a while now, so it's okay that I took a little break. I think. So, yeah, so you don't need to have uniform in front of like vectors. Actually, maybe you do. Actually, I think you do. Let's see what if that works or not. So it says unexpected thing on line 12. I don't really know what's wrong with that. I guess because the result doesn't exist anymore. So I'm just going to get rid of this. Because the result is a variable I got rid of. Let's test compile the shader. If you want to see how a shader works, I'm gonna get rid of test. Goodbye. I just wanted to show you what an unlit shader looks like, but in order to test if any shader works, you click show compiled code, and it doesn't work. So I gotta go and figure out what's wrong. If I look here, it says syntax error, unexpected integer constant. So Unity actually, shaders have their own little system in Unity, which is very powerful because there are different APIs for using shaders. There's OpenGL, there's Vulkan, there's DirectX, and all these APIs have their own shading languages. So they're actually, you have to code the shaders differently. And to make things more confusing, different graphics cards only support different APIs. So in order to get around this, Unity has its own language, which I'm coding in right now, called Unity Shading Language. And when I code in Unity Shading Language, the Unity program will take this language and it'll convert it into the other languages. And whenever you take one language and you convert it to another, it's called compiling. So that's what it does. It compiles the Unity Shading Language into the GLSL and HLSL, which are different languages for different APIs. So yeah, that's not good. So I gotta figure out what's wrong. This is an int. There's something seriously wrong with this. I don't know what. It's on line 12. Unexpected integer constant. I really don't know. So I'm just going to go here. I'm going to go size data equals float 3 1 1 1. I'm just going to put in some random code. I'm going to see if that fixes it. It did not. Well, actually, you have to recompile shaders. So I'm just going to run the game and recompile it, and it didn't fix it. So yeah, shaders get compiled differently. They kind of have to trigger it sometimes. I don't know what's wrong. I'm gonna have to Google this. It says unexpected integer constant. I've never seen this before. Shader unexpected integer constant Unity. This is Unity shading language, so I'm gonna make sure. That's a garbage character or something. That's not what I'm looking for. Also, my problem is though. This is really strange. Let's just copy all this. What is this? I'm going to go ahead and delete this shader. Delete, yes. I'm going to create new shader. Compute shader, and I'm going to call this map calculator. I'm going to paste this over here. Let's see what this does. Yep, same error. Okay, there's something messed up here. I gotta figure out what it is. Well, there is one thing I forgot. Maybe that's what the problem is. I'm gonna go to my old shader. Actually, no, I'm just gonna go here. And I have to go I have to add registers. I forgot this. I have to go register. This is T0. Registers are basically like little ports on the GPU. So I say what port I pass in this information. I had to put a different port for everything. So I'm going to go register U1. Ignore the letters. It just has to do with what type of data I'm sending in. I'm going to add a register for everything, and I'll see what it does. It might fix the problem. Yeah, shaders have a lot of really complicated things like this that are really hard to explain. I don't really understand it fully, to be honest. I just do it and it works. Let's see if that fixed it. I think that fixed the problem. No, it didn't. Let's see if I got rid of something or something. This is fine? Yeah, this is fine the way it was before. There's something different between this and this. So I'm going to copy this. I'm going to look at these two things top of each other, and I'm going to figure out which one is what's wrong with this bottom one that's not the same as the top one. I don't have a... Maybe it's a space right here. Let's try that. Yeah, that's not it. Maybe it's the space right here. Is there a space there in front of this? No, there's not. Shaders are very weird beasts that you have to understand. I mean, there's so many little things with them. I don't know what the heck is wrong with this. It has to be in the drive me nuts right now. If I get rid of these, I just try that. Does it have to do with the spaces? I mean, that would be really goofy if that's what the problem is. No, it's not. This is stupid. Okay, what? Maybe it's this comment after the pragma. Maybe that messes things out. Yeah, look at that. I fixed it. So you can't have a comment after a pragma. On the same lines as pragma. If I just put a comment here, it's not going to know what I'm talking about. Yep, you can't do that. That's interesting. So I can't have a comment there. Well, the more you know. I fixed that problem. That was annoying. Shaders, and that was a really good example of how shaders can be incredibly annoying sometimes. Because, well, they're just really ugly programs. They're not very clean. They're not very easy to code. They're just like, it's just pure raw code. It's just pure raw commands to the graphics cards. And it's just, there's a lot of weird things like register. Like most programming languages, they handle these things behind the scenes so you don't have to see it. But for a shader, it's all out in the open, and you have to code it all by hand. It's really annoying. yeah, that's why shaders are so difficult. Not because they're difficult in concept, but because, well, it's just the stupid way they're coded. And the reason they're coded this way is actually very important, though, I must admit. The reason that shaders have all these really weird things that are really hard to explain is because compatibility. So they want a shader that's designed for a modern graphics card to be able to work on an ancient graphics card at the same functionality, even though it won't work entirely because there's new features, but basic stuff will still work. So the old way they did things is the new way to do things, because they have to keep things working. So they can't just change the language entirely in a new update. They have to keep things really similar for compatibility reasons. So this has a lot of old stuff, and in languages like C#, they get rid of old stuff, but in shading languages, for some reason, they don't. So that's why it's like this. It's a little hard to explain why, but yeah, that's what they do. So I'm going to go back into the shader. I'm sorry for that little break where I was confused about that. I'm going to begin working on. I'm going to work on coding this shader. So I got CS Map Calculator, and okay, first thing I'm going to do is I'm going to calculate the height of this pixel. So it's, if you look at this shader, it has num threads 881. I explained this yesterday, but let's explain this again for the sake of clarity. This means there's 8 threads by 8 threads by 1 thread. It's making a 3-dimensional cube, I guess you could think of it like that. And so there's 64 threads running at the same time. So it's going to do 8 pixels by 8 pixels in a square of the. It's doing an 8 by 8 pixel square in the image at every instance. Instead of just doing a single pixel at a time, it does an 8 by 8 pixels square at a time. So it does 64 pixels at a time of the height map. And then we got this ID, SV dispatch thread ID. This variable can be used to refer to the pixel I'm currently at. So this function is going to run for every single pixel, and the only thing it's going to pass in is the ID of that certain pixel. So I'm just going to go float height. This is going to be the height of this pixel I'm currently at, equals, and now I got to figure out what the brightness of this pixel is. Now the best way to figure out the brightness is to take the R, the G, and the B values of the pixel color into account. So I'm just going to go height map ID dot XY dot R plus height map ID XY dot G plus height map ID dot XY dot B divided by 3 F divided by 3.0. Because I want it to be a floating point value, so you had to put the decimal there for shaders for it to know that. I can even just put 3 point and no. And then I'm going to multiply this times size data x. So whenever you see this weird thing where it says xy, ID.xy, okay, so the ID is actually a 3-dimensional vector. It's just like a vector 3. It's like x, y, z. Whenever I say xy, ID.xy, it's just returning the vector that's just x and y. If I said xz, it would return x and z. It would return zx, it would return the z, and then the x. It's just a shorthand notation you can do in shaders for grabbing vectors. So I'm grabbing the x and y positions, and the x and the y positions and the height map is this is basically a 2-dimensional array of the pixels. So I'm saying height map ID.x, ID.y grabs the pixel at x and y positions of the current thread. Yeah. and I divide this by 3, so I get the average of the red, green, and the blue, and then I multiply that times the height data, because by default this is a value between 1 and 0 and 1, and I want it to be a value between 0 and the size and the height limit, so it's going to be I multiply it times the height limit, and that works. Now let's make the vertices. So I'm going to go verts 3D, and this is interesting. I'm going to go id.x plus id.y times dimensions 1 dimensions.y. So I'm figuring out where. So if the vertices is a 3-dimensional array, is a single-dimensional array, and the entire map is 2 dimensions. So I gotta convert. It's just really hard to explain this without drawing it out, but I got to basically. Oh, let's draw it out. Actually, I don't feel like doing this anymore as a streaming. I don't feel like there's anyone watching. I think it's just me watching this because someone's commented. You know, this has been a great stream, but I'm really done now. I hope you guys are okay with that.